Hello, welcome to our video solution to problem 2 from Superquiz 3. In this problem, we want to compute the area of a parallelogram where we've been given the vertices. And to do that, we want to use the cross product. So a quick reminder about how this is going to work. If you have a parallelogram, so maybe it looks something like this. You know the four vertices of it. You pick any of the vertices, so I'm going to pick this one over here in the corner, and I can draw vectors along the sides emanating from that point to the adjacent points. And maybe we'll give a name to this, say this could be called U and this could be called V. And the way we're able to use the cross product to compute the area of this parallelogram is that the magnitude of the cross product is going to equal the area of the parallelogram. So the key here then is going to be to set up something of this form. And what we can do is to fix one of these points as one of these vertices. So how about let's go in order 1, 2, negative 1. So I have this point here, 1, 2, negative 1. And I'm going to connect it with a vector, right, to one of the other points. So there's going to be a vector, and I want to get over to 6, negative 1, 1. And to get there, let's see, the x-coordinate has to go up by 5. Right? A vector is just a shift, so that's what I do. Let's see, the y-coordinate has to go from 2 to negative 1, so that'll go down by 3. And negative 1 has to go up to 1, so this will go up by 2. Cool, so I get 5, negative 3, 2. All right, now this is my pivot point, so now I want to go to another point. All right, so this will be over here, and this, I'm not drawing it where they actually would be in the plane, but let's see. So this is going to go to 1, 3, negative 5. And what vector will I need to get there? So I need to go from 1 to 1. Well, actually, I don't have to shift at all in that direction. In the y direction, I have to go from 2 to 3. So we'll add 1. And in the z coordinate, I go from negative 1 to negative 5. So I go down by 4. So this gives me 2 vectors. And of course, this will generate now a parallelogram. And I can compute the area of that parallelogram by simply computing the cross product and then taking the magnitude. So I have the cross product of 5, negative 3, 2 with 0, 1, negative 4. And we actually found in the previous video this cross product. So I refer you back to that. You can get a link in the description. So there we found this will be the magnitude of the vector 10, 20, 5. So this will be the square root of 10 squared plus 20 squared plus 5 squared, which is, let's see, the square root of, 400, 500, 525. And that's a pretty good place to leave that. Now, a very reasonable objection to this is you might say, well, okay, if I just know that I have these 4 points and I start choosing 2 of them at random, how do I know I'm not actually getting the diagonal, right? What if I went from this point to this point? All right, well, that's a legitimate question. So let's see. Let's say I started with these 2 points and I actually computed this vector first. And then, well, I'm still using this as the pivot, so now I either connect with this one or that one. And let's say I connected with this one, so I get the same V here. Well, this is now going to generate a legitimately different parallelogram, right? So this will, you get this nice parallel vector here, and then it'll connect up with this copy of V. All right, okay, it's not a perfect parallelogram as I've drawn it, but okay, so we're looking now at this parallelogram instead of the original blue one. However, it won't matter for the purposes of this problem because you're getting a parallelogram with the exact same area. Why is that? Well, this is actually an old result of Euclid, all right, which says that if you take 2 parallelograms that have the same base, and you can see this V is common to both of them, so that's the base. And if you just slide the parallelogram over a little bit, so sometimes this is called shearing the parallelogram, you don't actually change the area of that parallelogram, because ultimately you're not changing the height, right? So long as we shear in a direction which is parallel to the original direction, or to the base, then we're not changing the height. The base is the same, and we know the area of a parallelogram is the base times the height. It's not how Euclid proved it. He used a lot of geometry to actually, well, really prove that the area of a parallelogram is the base times the height. Okay, so in any case, you won't get into trouble if you'd started by saying, okay, let me go from 1, 2, -1 to 6, 3, 6, 0, -3, and then I'll go to 1, 3, -5. You can work it out. You'll get the exact same magnitude at the end of the day because the parallelograms, even though they're different, have the same area.